All right, this is lecture 16.1 on pressure, part A, definitions. All right, so one of the important things when we talk about gases and gas laws, one of the things we'll talk about a lot is pressure. And so we should start by talking about what pressure means. So the question we want to ask is, what is pressure? And the simple kind of physics definition, pressure is a measurement of force distributed over an area. And we can write a mathematical equation for that. We can define pressure this way, where pressure is force divided by area. So we've got a simple mathematical definition here. Now, area, of course, is something that we're already familiar with. Force, perhaps a little bit less so. So let's go ahead and look at force for a minute. All right, so what is a force? The physics definition, and when you get into science, the more precisely you try to define something, I find sometimes the more obscure the definition becomes, and it becomes a little bit meaningless. So the definition given in a physics textbook is a force is any interaction which, if unopposed, causes an object to change its state of motion, causes an object at rest to begin to move, causes a moving object to begin to come to rest, or causes a moving object to change its direction, right, or speed, any of those things. But really, when you come right down to it, what we mean by force is really just a push, some kind of a physical push on an object. So, for example, if we look at this guy, moving this block here, right, he moves this by exerting a force on that block, right? Another common force that's important in chemistry is if you have two different objects, maybe they're two ions, one with a positive charge and one with a negative charge, then there's going to be a force of attraction between those two opposite charges. So it's a force that pulls one in that direction and a force that pulls that one in the other direction. Okay. Perhaps one of the simplest forces, and one of the first ones that was recognized, is just the force of gravity, right? I put an apple here because gravity is associated with Newton and the apple tree, the apple falling out of the tree and hitting him on the head, as the old story goes. But the reason that an apple falls is because there is a force pulling downward on it, right? And that force in this case is the force due to gravity. And it turns out that that force, the gravitational force, is one that's pretty easy to deal with mathematically. So to get into forces a little bit deeper, we're going to take just a minute or so and do some calculations with this gravitational force. All right, so let's look at gravitational force. Okay, when we're talking about force due to gravity, sometimes put a subscript G here to indicate gravitational force. And the gravitational force is equal to mg, where F is the force on an object due to gravity, m is the mass of the object, and g is the acceleration due to gravity. And acceleration due to gravity, at least on Earth, is a constant and has a value of 9.81 meters per second squared. So if we imagine doing a calculation to determine this force, we'd multiply the mass times this acceleration due to gravity, and our mass would be in kilograms, and the acceleration would have units of meters per second squared, and so we would find that our mass would have units of, our force would have units of kilograms, meters per second squared. Okay. And so this would be the collection of units that we should expect anytime we're calculating a force. And this collection of units.
Okay, just a simple reminder, spectroscopy, we've talked a little
Newton.
bit about this before.
So 1 kilogram
spectroscopy
per,
is the study of how light is
meter per
affected
second
by its
squared
interaction
is
with
equal
matter.
to 1 Newton.
And there are two things here that are important.
This
One is understanding light itself, but what's more important is that once we understand light,
unit,
we can use light to understand properties of the matter that it's interacting with. And that's what we're going to be interested in today.
All right. Now let's try our hand at doing a little calculation.
Okay, just a simple reminder, spectroscopy,
with a mass
we've talked a little
of
bit about this
125
before,
grams,
but
which is
spectroscopy
value for an apple.
is the study of how light is
know
affected by its interaction with matter.
Gravitational force
and there are
is
two things here that are important.
Pulling that
One
apple
is
downward.
Understanding light itself,
we can start
but what's
by
more important is that once we understand light,
equation,
we can use light to understand properties of the matter that it's interacting with. And that's what we're going to be interested in today.
Force is mass times the acceleration due to gravity. And our mass needs to be in kilograms. The mass here was given to us in grams, so we need to do a little conversion here. Okay. Our mass is 125 grams. Do a little metric conversion. There are 1,000 grams in 1 kilogram. So that means the mass of the apple is 0.125 kilograms. And G, we know that's a constant. G is 9.81 meters per second squared. So therefore, the force on this apple is 0.125 kilograms times 9.81 meters per second squared, which is 1.2263 kilograms meters per second squared. If we go back and look at our data, we've got 3 significant figures here. We've got 3 significant figures in this gravitational acceleration, right? So we should round our result to 3 significant figures, and we also can convert our units here. 1 kilogram meter per second squared is 1 Newton. So final result, the force would be 1.23 newtons. Okay, now that we've looked at force, we understand force, we can start to look again at pressure. We can go back to that definition that we had where pressure is force divided by area. And if we look at the units here, we just saw that forces.
Okay, just a simple reminder, spectroscopy, we've talked a little bit about this before,
and
but
spectroscopy
SI unit is the study of how light is affected by its interaction with matter. Right. And there are two things here that are important. One is
pressure
understanding light itself,
is going to be
but what's more important is that once we understand light,
and just as we
can use light
the collection
to
of
understand properties of the matter that it's interacting
with. New name,
and that's what we're going to be interested in today.
We can take this collection of values, collection of units, let's say. We can take this collection of units and rename this so that 1 Newton per meter squared is a Pascal. Okay, and Pascal is the SI unit of pressure. We'll see later in these videos that when we do things in chemistry, there are a bunch of other units that we use. We don't actually use pascals very often in chemistry, but it is the standard SI unit. So we should be aware of that, and we should see where that comes from here in this definition of pressure. All right, so let's
just a simple reminder: spectroscopy.
Pressure of some
we've talked a little bit about this before.
Object. Let's say we've got this iron bar,
is the study of how light is affected by its interaction with matter.
There's going to be,
and there are two things here that are important. One is understanding light itself, but what's more important is that once we understand light,
and if it's sitting on a table,
we can use light to understand properties of the matter that it's interacting with. And that's what we're going to be interested in today.
And that force will be transferred through the area in which they're making contact. Right. So if we want to determine the pressure that this bar exerts on the tabletop, that pressure is the force divided by the area. Okay. Area is not too tough. I think we can all. I think we can deal with that. Force is what's new for us right now. So let's go ahead, break this into two parts, and right now let's just look at the force. Okay. The force, of course, is the mass times the times g, right? Times the acceleration due to gravity. Unfortunately, this problem didn't give us the mass of the bar. It did give us the dimensions and the density. So with that, we can calculate the mass. Let's go ahead and do that. Okay. First thing we need is the volume, right? And the volume is just the length times width times height, right? So this is 4 centimeters times 4 centimeters times 10 centimeters, which gives us 160 centimeters cubed. Okay? And if we look at all of these values, we've got 3 significant figures and all of those values. So we want to write our volume in 3 significant figures. If we just write it this way, it's ambiguous. It's not clear whether it's 2 sig figs or 3 sig figs. So I'm going to use this notation that I like. It's very convenient. Put a little bar over a digit, and that means that's the last significant figure. So that's one way that we can write the volume and make it clear that we mean 3 significant figures. All right. Now, if we want to know the mass is the volume times the density. Okay. So this is 160 cubic centimeters times 7.86 grams per cubic centimeter. You can see that our cubic centimeters are going to cancel out, and that gives us, let's see, 1,257.6 grams. Okay, and we did this on the previous calculation. We need to put that into kilograms. So let's go ahead and do a quick calculation here. 1,257.6 grams. Remember that 1 kilogram is 1,000 grams. So this tells us 1.2576 kilograms. All right. And again, since we had 3 significant figures here and 3 significant figures here, this value here we should write to 3 significant figures. Instead of rounding it off now, I'm just going to put that bar over it to remind us that this mass is correct to 3 significant figures. Okay.
Okay, just a simple reminder, spectroscopy.
We're making a lot of progress.
We've talked a little bit about this before, but spectroscopy is the study of how light
there.
is affected by its interaction with
Determined that
matter.
the mass of
And
this
there are
iron
two
bar
things here that are important.
is
One is
1.2576
understanding light
kilograms.
itself, but what's more
Did the three
important is that once we
figures.
understand
So
light,
now we can calculate the
we can
force.
use light to understand properties of the matter that it's interacting with. And that's what we're going to be interested in today.
The force that this exerts on the tabletop is the mass times the acceleration of gravity. And G, of course, is a constant. And if we multiply those together, we get 12.375 kilograms meters per second squared. Okay. We've got three significant figures, and the two things we're multiplying, so we should have 3 sig figs in our result. And we can also simplify this a little bit by changing that collection of variables to newtons. So the force exerted by this iron bar is going to be 12.4 newtons. Okay.
Okay, just a simple reminder, spectroscopy.
Almost ready to calculate
We've
the
talked a
pressure
little bit about this before.
exerted by this
spectroscopy is the study of how light is affected by its interaction with matter.
And
there are two things here that are important. One is understanding light itself, but what's more important is that once we understand light, we can use light to understand properties of the matter that it's interacting with.
And we know that,
and that's what we're going to be interested in today.
Pressure is the force divided by the area through which that force is acting. And for this particular object, this iron bar, the iron bar is resting on a table, and so the surface through which that force is acting is that area of contact between the iron bar and the table. And that surface has dimensions of 4 centimeters by 10 centimeters. Okay? So we can calculate that area. The area is just 4 centimeters times 10 centimeters, which is 40 square centimeters. Okay, and that's correct. It gives us a little bit of a problem because when we put our units in to do our calculation of pressure, this area down here needs to have units of square meters, and we've got square centimeters. So we're going to have to do an extra little conversion here. It's not tough, but there is a little trick to it. So let's take a look at that. If we have 40 square centimeters, we want to convert this to meters. We can do simple metric conversion. Right? There are 100 centimeters in 1 meter. Okay? But if we do that conversion as it is, we've only got 1 centimeter down here in the bottom, and we've got centimeters squared over here in our starting value. Right? So in order to cancel both of those centimeters, we need to do this conversion twice. And so we'll put 1 meter is equal to 100 centimeters twice, and now these two instances of centimeters cancel out centimeters squared, and because we have meters in there twice, we get meters squared for our result. And so our answer is 0.001 0.00400 meters squared. And now we're almost there. We can calculate our pressure. Pressure is just force divided by area. And we've already calculated our force, which is 12.4 newtons. We've calculated our area, which is 0.00400 meters squared. If we put that in the calculator, we get 3,100 newtons per square meter. And we said before that this collection of variables, collection of units, newtons per square meter, is 1 Pascal. So we could rewrite this as 3,100 pascals. Right? And we've got 3 significant figures and all the things we multiplied together. So we should write our result with 3 significant figures. We can write it that way with a bar over it. We could also, so a couple of different ways we could do this. We could say 3,100 pascals. We could write that. Or we could write, we could use scientific notation, 3.10 times 10 to the 3 pascals. Or if we wanted, we could use a metric prefix and say 3.10 kilopascals. Any of those would be acceptable answers for this one. All right, terrific. So there's a lot of steps in that one. I think all of the steps individually are pretty simple, but there's a lot of parts to putting that whole thing together. I feel good with the work we did on that one. Let's take a look at another one. Okay, here's the similar problem. It's actually the same iron bar, right? But now instead of lying on its side, we've tipped it up so that it's standing on its end. And what I'm going to ask you to do is go ahead and in a minute turn off or hit pause on the video and calculate the pressure that this iron bar is exerting on the tabletop if instead of lying on its side, it's lying on its end. Okay. The rest of the problem is exactly the same except for the orientation of the bar. Okay. All right. So go ahead and hit pause and work through this, and then check back, and we'll compare our results. Okay. Now, because most of the parts of this problem are the same, the dimensions of the bar are the same, and so because the dimensions of the bar are the same, the volume is the same, so it still has a volume of 160 cubic centimeters. Okay. And with the density, what it is, that means that it still has the same mass, so you should have calculated a mass of 1.2576 kilograms. If you want to round that to 1.26 kilograms, you can do that if you want. I try not to round things prematurely. Try to keep a few extra digits in the calculator until I get to the very end. But it's not tragic if you round that off in the middle of your calculation. And since the mass is the same, the force is mass times the acceleration due to gravity, which is a constant. So, of course, the force should be the same also, right?
Okay, just a simple reminder, spectroscopy, we've talked a little bit about this before, spectroscopy is the study of how light is affected by its interaction with matter.
Gotten the same
and there are two things here that are important. One is understanding light itself, but what's more important is that once we understand light,
now, if we want to calculate
we can use light
pressure,
to understand
all we have to do
properties of the matter that it's interacting with. And that's what we're going to be interested in today.
The area. And the area in this case is different. So that's where we're going to have to change our calculation a little bit.
Okay, just a simple reminder. So spectroscopy, we've talked a little bit about this before, but spectroscopy is the study of how light is affected by its interaction with matter.
And that force
is exerted over the surface here. And there are two things here that are important. One is understanding light itself, but what's more important is that once we understand light
of that surface,
we can use light to understand properties of the matter that it's interacting with. And that's what we're going to be interested in today.
Times 4 centimeters, which is 16 square centimeters. And we can do that same conversion that we did last time. Converting square centimeters to square meters. We'll use our standard metric conversion. 1 meter is 100 centimeters. Right? But because of the square in the units, we've got to do this twice. And this gives us 0.00160 square meters. Right. Then to calculate the pressure, of course, is just the force divided by the area, which in this case is going to be 12.4 newtons divided by 0.00160 meters squared, which gives us 7,750 newtons per square meter. And of course, a newton per square meter is a Pascal. So the pressure exerted by the iron bar in this orientation is 7,750 Pascal. And that's already got 3 significant figures, so that's fine. If you wanted to, you could write this as 7.75 kilopascal. That would be fine too, although you don't need to do that. Either of those answers is perfectly fine. Alright, so let's look at where we're going.
Just a simple reminder, spectroscopy, we've talked a little bit about this before, but spectroscopy is the study of how light is affected by its interaction with matter. Where we're going with this is eventually, and there are 2 things here that are important. One is understanding light itself, but what's more important is that once we understand light, we can use light to understand properties of the matter that it's interacting with. And that's what we're going to be interested in today.
Those little dots are gas molecules. And so you might imagine someone putting a little weight on here, and that weight would exert a force down on that piston, and the piston would move down a little bit and compress that gas, and we could do a calculation based on the mass that's pushing down on the gas, and we can calculate the pressure of that gas. That's ultimately where we're going with this. Okay. Conversely, another way to look at this would be we could have a cylinder like this, and the cylinder maybe is hooked up to some kind of a drive shaft and a bunch of gears or something, and the gas, maybe we heat up the gas, that creates a pressure, and so instead of having the piston pushing on the gas, we can think of the gas pushing on the piston, and that would create some kind of an upward force. That's the kind of thing that would happen in an internal combustion engine or something like that. So we started by talking about just forces and pressures, looking at simple solid objects, little prisms and cubes and things like that. But ultimately, the reason for discussing that is so that we can get to this and talk about how that would impact the pressure of a gas in some kind of a similar situation. Alright, so here we are at the end of this first video. Okay, what did we go over in this one? Okay, first of all, we talked about the force of an object due to gravity. There are several different kinds of forces, electrical forces, magnetic forces, so on and so forth, but the easiest one to deal with so we tackled that one in this video, is force due to gravity. And force due to gravity is the mass of an object times this gravitational acceleration constant. And when you multiply this out, you'll see this set of units, kilograms meters per second squared. This set of units is redefined as the Newton, which is the SI unit of force. And then we also talked about pressure. Right? Pressure is this force distributed over an area. This is an important equation. This is the definition of pressure, so you should be familiar with that. And when you do the calculation with pressure, you find that you end up with newtons per square meter.
Just a simple reminder, spectroscopy, we've talked a little bit about this before,
is defined
spectroscopy
as
is the study of how light is affected by its interaction with matter. And there are two things here that are important. One is understanding light itself, but what's more important is that once we understand light, we can use light to understand properties of the matter that it's interacting with.
A couple simple calculations.
And that's what we're going to be interested in today.
On pressure, you want to make sure that you can repeat those types of calculations. And then once you've got that, we'll move on and start looking at pressure in gases. That'll be the subject of the next videos.